In this video, we're going to do another fluid force example. So we have a submerged semicircular plate. A semicircular plate, 2 feet in diameter, sticks straight down into fresh water with the diameter along the surface. Find the force exerted by the water on one side of the plate. So our fluid force formula, we're going to say F is going to be the integral from A to B of W, my weight density for whatever liquid we are dealing with, times my strip depth, times my length equation, which can vary. It's going to be a function of y, integrated with respect to y. So let's think about what we're looking at here. We have a semicircular plate. I'm creating an axis, and it is submerged in the water. So it has a 2-foot diameter. So 2-foot diameter means from edge to edge on this semicircular plate, that's going to be 2 feet wide. So if I were to create, considering this one point being the origin, 0, 0, create an axis here, I could label this point as 1, 0, and this point as -1, 0. Also, the point at the base would be 0, -1. All right, and it says that the diameter runs along the surface, right? The diameter is going along the surface. So we know we're right up here at 0, 0. It's not submerged down below the surface. So first thing we need to do is come up with an equation for this shape. And this shape is the bottom half of a circle, radius 1, right? So we're going to need to come up with our length equation. So we need to figure out a way to represent this depth. And this is the bottom half of a circle. So the equation of a circle, radius 1, would be x squared plus y squared equals 1. And since we want that equation to be x in terms of y, we want to function in terms of y, we're going to isolate x, so my y is all on one side of the equation. So we would have x squared equals 1 minus y squared, or x equals plus or minus the square root of 1 minus y squared. So that plus or minus, that is the right or the left half of the equation. And if I throw the minus away, right, so that was giving me this piece of the circle, the plus. Throwing that minus away is getting rid of this half of the circle over here. Okay, so we only need the right half of the circle, not the left half of the circle. So I'll just rewrite that as positive. We've got the square root of 1 minus y squared. So we use the plus minus when we're solving, but that's giving me both halves of the circle, and we only need the right edge. So this guy represents our right edge. And you'll notice that it is x in terms of y. So the strip length, though, the length of that strip all the way across is going to be 2 of those. So when we look at doing this, the strip length, we're going to say that Ly is 2 of that square root of 1 minus y squared. All right, my bounds for my integration here, my a and my b values are going to go from -1 to 0. So my y interval is from -1 to 0. The strip depth, since we are traveling down vertically, my strip depth is going to be -y. And because this is fresh water, my weight density W is going to equal 62.4. and that's pounds per cubic foot. So now that we've drawn our picture, we've analyzed our problem, let's set this integral up so that we can solve it. Got all this extra information here. So my fluid force is going to be the integral from -1 to 0. My weight density, 62.4. My strip depth is -y. My strip length is 2 times the square root of 1 minus y squared. And we need to integrate that with respect to y. So the 2, the negative, the 62.4, I can pull that all out in front, which gives me -124.8, integral from -1 to 0 of y times 1 minus y squared to the 1/2 dy. So pause the video, make sure you understand everything I have done up to here, because at this point, we've set it up and we're going to solve this just using a basic u substitution to find this integral value. Okay, so when we're doing a u substitution, I am going to say I'm going to let u equal 1 minus y squared. And if I do that, that's going to change my bounds of integration. If I plug in -1, I'll get u equals 0. And if I plug in 0, I get u equals 1. So I'm plugging both these two numbers into that equation. And then I will differentiate u with respect to y. That gives me -2y, or rather -1/2 du equals y dy. So let's set this up. Let's see, I've got -124.8. My integral now goes from 0 to 1 instead of -1 to 0. My u, what's in the parentheses, is 1 minus y squared. That becomes u. I have u to the 1/2, and y dy is equal to -1/2 du. So I'm going to put that -1/2 in the front and my du here. So cutting that value in half, I'm going to have 62.4, the integral from 0 to 1 of u to the 1/2 du. And because I changed my bounds, there's no reason that we need to go back to any y values here. So I'll use the power rule to integrate this, which gives me, adding 1 to 1/2, gives me 3/2. So I have 2/3 u to the 3/2 from 1 to 0. When I plug 0 in, that's obviously going to 0 out. Plugging in 1 to the 3/2 will remain 1, so we'll just get 2/3 here. And 2/3 of 61 or 62.4 is 41.6. And that's 41.6 pounds. So hopefully you understand fluid force against a plate a little bit better at this point. As always, email me if you have any questions.